Hello everyone, welcome to Naked Mole Rat Productions with Adele and Charlotte. Yes, physics, yes, fun.
Hi everybody, my name's Adele.
And I'm Charlotte.
We're going to learn about a crash.
Where are the wheels?
Who did it?
You did.
And scene cut.
Everyone. So, in today's episode of Investigative Crash Blame Placing, we have a very peculiar accident that occurred between Mr. Garcia and Miss Wakefield at the intersection of Taft and Dallas Streets in Houston, Texas, between a compact car driven by Mr. Garcia and a tractor trailer driven by Miss Wakefield, as you can see by the artwork being performed on the screen. At this intersection, the truck driver had a flashing yellow light, while the car driver had a flashing red light. And neither driver is claiming responsibility for this action. So as you can see, there was a collision. And by the lines drawn, you will see the directions of both of the cars post-crash. Now, it remains our job to solve this crisis and to figure out whose fault it is. So as you can see, the car left at an angle of 33 degrees and the truck left at an angle of 7 degrees. Boom! Who did it? Miss Wakefield? Mr. Garcia? Who knows? Who done it? So our first step here is finding the coefficients of friction for both the car and the truck, because these are going to be essential to determining our pre-collision velocities. So the first step is to draw a free body diagram of the car. So the car weighs 13,600 newtons. And according to the police department, it requires 100 newtons to drag a 130 newton tire across a road. Now this is important because this is going to give us the force of friction, and it's going to help us find the force of friction. And the reason why we're using mu s in this equation is because it was determined that the car was skidding. Now, because static friction is a lazy force, it is 100 newtons on the other side as well. So by doing a handy-dandy little mathematical equation, we are able to determine the coefficient of friction for the car. Check it out. Now, for the coefficients of friction for the truck, specifications from the truck manufacturers give us information that they're only 70% that of the car. So, quick little calculation to give us the coefficient of friction for the truck, as you see on the screen.
Alright folks, so next comes the acceleration. For starters, we're going to draw a nice little free body diagram and apply Newton's second law to make sure we are accounting for all of the forces present. The car weighs 13,600 newtons, and we found the coefficient of friction, so now it's time to apply those things by using the formula F of F equals mu SFN, and then we get the force of friction. Now, this is the only force acting on a car in this dimension, so by setting up Newton's second law equation, we are able to determine the acceleration of the car, and then we're going to apply the same exact principles to the truck in order to find its acceleration. Find the force of friction, set up your Newton's second law equation, and solve for the acceleration. It's as simple as that. So here we are again, drawing yet another free body diagram to help us find the force of friction for the truck this time. This is going to help us find the acceleration, and then we can see who done it, but not just yet. We're still going to have to look through the pre-collision and post-collision velocities. Oops, made a little mistake there, but that's alright, we're human.
Okay, team. So in this part, we're going to find the pre-collision velocity of both of the vehicles working in the x and y dimensions. Now you're going to see us using some numbers that we haven't calculated yet, but have no fear, those calculations are coming right up after this. So after the collision, the cars moved both at angles, which means we have to deal with x and y components. So we're going to start off by just focusing on the x component and using the law of conservation of momentum to make sure that we're not losing anything or adding anything. So the only thing that was moving in the x direction before the collision was the truck driven by Miss Wakefield. But afterwards, we have to account for both of the things moving at an angle and make sure that we're not losing their velocities or their momentums. So as you can see, we're just plugging in numbers and using the variable v2 to represent the initial velocity of the truck. And after doing some simple calculations on your trusty TI-84 calculator, and a few errors made by us, you are able to see that V2 is 12.502 meters per second. Excellent stuff. And now we're just going to do the exact same concept, the law of conservation of momentum, but instead of using cosine, we're going to use sine because this time we're operating in the y dimension. The same process of plugging in numbers that we're going to be calculating right after this to find our simple solution of, wait for it, 12.24 for the truck. Excellent. Love it. Nice. And lastly, for the post-collision velocities, which is where those other numbers that we were using in the pre-collision velocity are going to be calculated. And for this, we're just going to use some handy-dandy kinematic equations because luckily some information was given to us investigators by the police department. So we know that both cars came to a full stop afterwards, and we know their acceleration, which we calculated earlier, and their distance was given to us by the police department. So by having that information, we're able to do some pretty easy calculations of both the car and the truck for their velocities. Love it. All right, folks, now this is where things get interesting. This is where it becomes our job to place the blame. So let's look at some statements that the truck driver and the car driver claim to make. So the truck driver, Miss Ann Wakefield, claimed that she was only traveling 6.7 meters per second at the moment of impact. However, according to our calculations, the initial velocity of the truck is 12.502 meters per second, virtually double what she claimed to be going at. Does anyone else smell fish? All right, and then another interesting fact. According to the Ford Motor Corporation, the maximum acceleration of a comparably loaded Ford Escort is about 3 meters per second. So that means that if your initial velocity was 0, which, according to the driver of the car, who claimed that at the moment of impact he had made a full stop and was only traveling 0 meters per second, that his maximum velocity would be 3 meters per second, going from 0 to 3 in 1 second. Are we on the same page? However, folks, we found that his acceleration was actually 7.56. That was the acceleration of the car post-collision. So it is obvious that he had to be starting at some velocity that was greater than 0 for him to be getting to 7.56. So, who done it? They both did. Case closed. See us next week.